bonus lecture. In Rowell and Wormley, problem 13.9a, now this is the figure from that problem, you are asked to write the transfer function from an input velocity source, so Vs, to the velocity of the mass, Vm. So or we would write this as Vm over Vs, both of these being functions of s, but sometimes we drop those function of s characters there. So we want to know what this is. So how do we proceed? I'm going to proceed first off by drawing a linear graph. So I think that you guys are all working on this on your homework and doing just fine on this part, but it's always good to be thorough. So we have our ground node here. We have a velocity source, I said, so we can draw that in. Vs. We didn't draw our coordinate arrow direction. Let's draw in the direction of the velocity source so that we're all good. Drawing the arrow down to ground. We have our spring K. Goodness. And then we have mass node, which is always going to connect to ground. And we also have a damper that connects to ground as well. So that is our linear graph. I'm going to use, so we're obviously going to use impedance methods, but the two routes that we have available to us, the sort of standard one that's shown in the textbook in section 13.4, and there's also this cross-variable divider, through variable divider sort of shortcut that we have, and that's definitely the way to go on this problem. So I'll show you that. So we have an across variable source related to an across variable output, so Vm to Vs. So we want to know the velocity of the mass. Fortunately, we can write this circuit as an equivalent circuit with, I'll write the equivalent to the left. So we've got Vs still, so let's draw an equivalent circuit with K still in place, and with these two elements that were in parallel here, M and B, combined into an equivalent impedance. I'll just do it Z, let's do ZE. And this circuit or graph, the across variable divider rule can be applied directly to it. We can find the relationship between Vs and VZE very easily because it just has two series impedances here, just like the voltage divider. This circuit is, or this linear graph is a little bit tougher to look at, but what we can see from it is that the cross variable across ZE is equivalent to the across variable across M. And so that's why this is going to get us very close to our answer if we use this equivalent circuit. So maybe I'll do step 2, arrange, and I'll make this the arrangement here. Step 3 is to use the across variable divider rule. Which states for this case that VE, which is the cross variable across ZE, over VS is equal to the impedance of E, so ZE, divided by the sum ZE plus ZK, the other impedance in series. And let's go ahead and plug that in. Z equivalent, so if we have M and B here, we need to know what those what ZE is. So maybe I should put that up here. What is ZE? ZE is equal to, in parallel, you combine them in the fashion, we're going to use the little shortcut formula, ZM ZB divided by ZM plus ZB, and if we plug in the impedance of each, if we forget what those impedances are, we can always go back to the elemental equations, or don't forget about this nice handout on the website. So we have a mass and we have a damper. So the mass impedance is 1 over ms. The damper impedance is 1 over B. So we have 1 over BMS divided by 1 over MS plus 1 over B. And that, we can simplify down a little bit, is going to be equal to 1 over, so BMS, the S's and the M's cancel, so we have a B here. And we have, in the second term, we have the B's cancel, and there's an MS plus MS. Okay. So that is our impedance for the equivalent parallel. So we plug that in for ZE here, and we have 1 over, I'm going to switch the order, MS plus B divided by 1 over MS plus B plus, this is the impedance of the spring, which, going back to our cheat sheet, is S over K. S over K. Alright, so to simplify, let's drop this denominator down to the denominator, the other denominator. Move this just a little bit over so we don't squish it here. So we're going to get 1 over, and the MS plus B cancels on the first term, and then in the second term we have everything will be over K that remains, and we'll have M over K S squared plus B over K S. we multiply top and bottom by k, sorry for crowding that there, we can get something that looks like k over, simplifies a little bit, rearranging terms a little bit, ms squared, just to get the polynomial in descending order of s, plus bs plus k. All right, so that is our transfer function from vs to ve, but we want to know what it is from vs to vm. And vs to vm, we have to recognize that so rewrite without equivalence. We have to recognize that our Vm is equal to Vze or Ve, right? So Vm, which is what we would like to get it in terms of, is actually just equal to Ve. So our final transfer function is just Vm divided by Vs equals k over ms squared plus bs plus k. And if we wanted to rewrite it in sort of standard form, which means that the denominator polynomial has a 1 in front of its highest order term, we would divide the numerator and denominator by that term here, which is m. So we'd have k over m divided by s squared plus b over m s plus k over m. And from this we could recognize things like the damping ratio and the natural frequency of the system. So that is how to do it. Yeah, if you have any questions, let me know. So this is our transfer function. This is our answer. All right. Peace.